Hey everybody, it's Miss Landry. Welcome to video 2 on cellular respiration. In the last video, you learned about glycolysis. Here's our mitochondria shown here. This is a nice electroscanning micrograph of it. You can see the cristae is the pink here, and then around that, the spaces that you see, that is the matrix. So that is what we're going to be talking about now. So we're going to talk about the Krebs cycle, or what's also known as the TCA cycle, which stands for the citric acid cycle. So this is going to occur in the matrix of the mitochondria. Now, before we get into the actual cycle, we do have to talk about this kind of intermediate step. If you remember from glycolysis, we ended up with pyruvate. So one glucose molecule is going to create two pyruvates, if you remember that from the last video. So we have a pyruvate here. If you remember, it's a 3-carbon molecule. So when it enters into the space of the mitochondria, there's a little kind of intermediate step that occurs. The first thing that happens is NAD, which we can see here. This is very similar to the NADP from photosynthesis, a slightly different molecule, but it has the same function. Here, if you notice, it is going to be reduced. So we're adding electrons, we're stripping electrons off of the pyruvate, adding them to the electron shuttle of NAD+, which makes it NADH. In addition, we are also losing a CO2. So a CO2 molecule, which is waste, is going to be kicked off, which means that we now have a 2-carbon molecule. So we went from 3 carbons, we're now down to 2. In this intermediate step, when we reduce NAD, we're also adding another molecule called CoA. So when we get this 2-carbon molecule plus CoA, we get a molecule called acetyl-CoA. So this is kind of the intermediate step, but it is important because we've already got one electron shuttle that's going to be used in the third phase, and we also have a waste product of CO2. So that is important to know. But now we're going to go right into the cycle. Now don't get scared by this. I know it can be a little bit scary to see all this stuff, but this whole thing right here, this is our intermediate step that we already went into. So if you notice, we have acetyl-CoA right here, and I want you to look at how many carbons we have. We have 2 carbons entering into the cycle. Now this is going to add with a molecule called oxaloacetate. Just going to write it out here, and you can see we also call it OAA. And that oxaloacetate is a 4-carbon molecule. So I have a 4-carbon molecule joining with acetyl-CoA, which is a 2-carbon molecule, to give us how many? You got it, 6 carbons. Now that, if you can see right here, is citric acid. That's where we get the name of this cycle, citric acid cycle. So we have a 6-carbon molecule. We're going to go into the cycle, and I want you to notice the first thing that's going to happen is we are going to reduce NAD+, whoops, that should be an E. So reduce NAD+ by stripping electrons off of the citric acid. We're also going to kick another CO2 off. So we've had one CO2 from this process at the top here, from this intermediate process. We have a CO2 molecule getting kicked off here. So far for the pyruvate, we've got 2 CO2 molecules being kicked off. If I kick off that CO2 molecule, I am down to 5 carbons. Now, as I keep going, notice I'm going to reduce NADH again. So I've got another electron shuttle. I'm stripping more electrons off of this carbon molecule. I'm going to kick off another CO2. I'll try to color it the same. So that's my 3rd CO2 that I've kicked off. So far we have 3 CO2s that have come out of this. We have also reduced NAD once, twice, 3 times. Well, here's the 4th, but hold on, back up a little bit. We're not actually doing that. We're going to phosphorylate here. Notice we take ADP, we're going to add a phosphate to it and create ATP. So that now we have an ATP. We're going to keep going. Remember, we've kicked off that CO2, so we are now down to 4 carbons. So we have a 4-carbon molecule here. We're going to strip more electrons off of it, and we're going to reduce FAD. Now, don't worry about the name FAD. You are correct that it is not NAD. It is a different molecule, but it has the exact same function, okay? It is going to shuttle electrons to the electron transport chain. Notice we reduce another NADH here. So all we're doing with this whole cycle is we are basically taking the electrons off of this carbon molecule. We're getting rid of some carbons through the process of making waste products of CO2. We have made an ATP down here at the bottom. It's kind of hard to read that. And then the most important thing is the amount of electrons that we have stripped from this molecule, and we're going to shuttle those electrons to the next step, which is the electron transport chain. Notice at the end of the cycle, we have 4 carbons here. So we have now basically regenerated oxaloacetate, which is what we started with, similar to in photosynthesis when we regenerated RuBP. So I hope that makes sense. We can go through our kind of ins and outs here like we always do. So here, let's look at what we have coming in. I'm not going to do the intermediate step. Let's just do the cycle. So what we have coming in is acetyl-CoA. Okay, that's going to join with oxaloacetate. Okay, and from that, we're going to get, let's see, how many NADHs? 1, 2, 3 NADH will be reduced to 3 NAD pluses will be reduced to NADH. So that means we had to have 3 NAD pluses. We're also going to reduce 1 FADH to FADH2. So we had 1 FAD. And then we are going to take 1 ADP, which we started with, and a inorganic phosphate, and we're going to make an ATP. In addition, we are going to make oxaloacetate at the end. So those are our ins and outs. We kind of still end up with the same amount of carbon that we started with, and that's the key. I hope this made sense. I will also include a video, so if this is confusing, you can certainly watch this again, or you can watch another video. Thanks, guys. Hope you're having a great day.